Welcome to today's lab session, where we'll be determining the molecular formula of a hydrated iron 2 sulphate solution. In this experiment, we'll focus much on how to determine its molecular formula by using a standard solution. And also, it is important that you go through the data analysis section, which we'll use to determine its molecular formula by determining its empirical formula mass.
Alright, thank you so much, Ms. Wale, for that. And like mentioned, this is the last lab that we're trying to work on, and we're trying to touch the aspect of the redox reactions. And then something very significant that we need to understand from here is that there are certain things that we get to focus on, specifically seeing how best we can balance the number of electrons and also balance the number of atoms in a redox reaction. And then something that we should also understand is that when you're working on the aspect of the redox reactions, you get to do it based on what we call the half reactions. So you can see the first part of the half reaction has been given, the second part of the half reaction has been given, and what is important here is coming up with the overall half reaction to the entire equation. So now, how do we do that? So the first half reaction has been given as 1.50, that's the initial, and the second part of the half reaction, the initial has been given as 0.77 volts. And what we're simply trying to do here is come to something that is the overall reaction. So what do? You identify the first part as a value of 1.50, the second value as a value of 0.77. The smallest figure between the two is 0.77, meaning that we're reversing the second part of the half reaction. And after reversing that, what are we supposed to do? We come here. We are balancing the number of electrons and also balancing the number of atoms. So you can see from the first part of the half reaction that we have one atom of the iron here on the side of the reactants, and on the side of the products we have one atom of the iron. The number of electrons balanced for the first part of the half reaction and the second part of the half reaction. There's a 1 here, there's a 5 here. So how do you balance them? Of course, the 5 is multiplied out throughout the course of the entire half reaction, and then there's a 1 there. So now you've balanced that. When you get back to the concept of the redox reactions, I guess you get to understand how we were trying to form this. So the end reaction is right here. So in the entire course of this lab session, what we're simply going to focus on is this. This is what is relevant. To find out the moles of the potassium permanganate, to find out the concentration of the potassium permanganate, this is what we're going to be using. And when you get back to your lab man, you're going to be given something very significant and something very important that they're pointing out. These formulas that are here. Meaning that when you get back to this equation, there's a more ratio here. There's a more ratio of 1, and then there's a more ratio of 5 here. So meaning that there's 1 mole of the magenta that is reacting with the 5 moles of the ions. So basically, we're trying to see how best we can come up with different kind of figures to see how we can drive the formula of the iron hydrate solution. Okay, so we're now back in the lab session. We're trying to discuss the technicalities of procedure, trying to see which reagents we're working with. And then one thing that we should understand from here is that the first part has already been done. When you get back to your lab manual, the two most important parts we're supposed to focus on is part A and also part E. So the first part of the A was
standardizing the potassium permanganate, but it has already been standardized for us.
Okay, so the concentration of the potassium permanganate that was standardized and given in the question was
0.02 molar.
Exactly, so 0.2 molar. So we know that the titrant which is already in here is 0.02 molar. And we're trying to use this to find out the concentration as well as the moles of the iron 2 sulfate. Okay, and then now she's going to clearly explain to you how you're supposed to mix and what you're supposed to do when you get into this lab session.
Okay, so the first thing that we have with me here in the conical flask, we have this iron 2 sulfate, which is mixed with the sulfuric acid. So as mentioned earlier, we're having this entire experiment being done under acidic media. Also, we're having the sulfuric acid in here so as to prevent the oxidation of the iron 2 sulfates. Okay, this is the sulfuric acid in here, and as explained, this is already standardized potassium permanganate. Okay, so at first, there is need to record the initial volume there, and making sure that you read the volume from the upper meniscus because it's colored, the solution is colored. Okay.
Alright, so Ms. Waya here is going to give us a clear demonstration of how the lab will be done. So like you emphasized, we have made sure that what is in the conical flask there is the iron 2 sulfate mixed with the sulfuric acid. And at the end point, what do we expect?
We expect a purple, faint pink color. Yeah, because the potassium permanganate is self-determining. There is no need for an indicator because it already has that everything.
Alright, so we can go on with the titration.
With me here in the conical flask, we have the iron 2 sulfate, which is mixed with sulfuric acid. So we're mixing it with the sulfuric acid in order to prevent oxidation of the iron 2 sulfate, and also, okay, we can now start the titration. And as mentioned earlier, we're recording the volume from the upper meniscus because the solution is colored rather. Okay, making sure that our eyes are focused on the conical flask. Hi guys, don't forget to join the Pomboloka movement. Remember, Nala Pomboloka, Wala Pomboloka, Wala Pomboloka.